Hello everyone, welcome to my first episode in my practical guide series. Today we're going to be looking at the Hugging Faces transformer library, going through some of the basics. In future episodes we're going to be going on to some more advanced topics, taking some of the language models from the transformers library, retraining them and applying them to our own downstream tasks. So stay tuned for that. So in today's episode, as I said, we're just going to go through some of the basics. And the basics include what is the Hugging Face Transformer Library, what can it do. We're going to be looking at how to navigate their website and having a look at their documentation. When I first found the Transformers Library and was trying to use it for some tasks, I thought there was a bit of a lack of a sort of a guide on actually focusing on how to implement these models, how to navigate their documentation. So that's what we're going to be trying to do today. So we're going to get some of these Hugging Face models, these language models from their website or from the library, and applying them to some very simple examples at the beginning. In future episodes we're going to be training our own models and applying them to our own tasks. So let's jump in. So let's start just on their website. So I'm just going to go to huggingface.co. So what is Hugging Face? So Hugging Face is a company, their most sort of successful product is this thing called the Transformers Library. So you can have a look on the GitHub. Hugging Face Transformers. It's got a bunch of favorites, a bunch of stars and stuff. So what can you actually do with this library? Well, their sort of main purpose is to sort of offer this platform to access these large language models. So and they're all based off the Transformers architecture underneath, which is why it's called the Transformers Library. So let's just have a little look at some of their models that they offer. So these are their most popular ones at the top. So BERT based on case, distilled RoBERTa, RoBERTa base, distilled BERT. So what does this all mean? So back in sort of 2017, I think it was 2017, the Attention is All You Need paper came out, which was the first sort of paper to apply the Transformers architecture to a language model. A year later, I think it was 2018, but I have to double check. The BERT paper came out. So what does BERT stand for? BERT is the bidirectional encoding representation from Transformers, and it's a large language model trained on a masked language modeling task. And it's trained on gigabytes and gigabytes of text data. So the model comes in a couple of flavors. It comes in a base and a large version. So the base is has got a smaller set of weights or parameters. The large has a larger set. So the large is going to be more effective, but you have a training overhead and inference overhead of processing all the weights and parameters in the model. There's also, for BERT, there's an uncased and a cased version. So whether you're going to be using capital letters or not. So yeah, you're going to want to pick what's right for your task and what sort of compute power you have. There's also the distilled versions of these models. So the distilled versions are basically just a same model, but with a much smaller set of weights and parameters. So faster inference, faster training. You suffer, of course, a little bit of performance, but it's not that much. So you can weigh that up for your use case. There's also the RoBERTa models, which stand for the Robustly Optimized BERT approach, which was released, I think, 2019 by Facebook. And that is basically a BERT model, trained in a slightly different way, trained on for a much longer time, on much more text. And there's a few other special techniques they did whilst they were training to massively improve the performance over the base BERT model. So RoBERTa, I think, is always case. So you just have the base model, you have the large model. So let's have a little look at just the BERT base model, the most popular model they offer, and let's jump in. So over here, so you can read the model description, you can read the paper if you like. So it's focused off this paper and it will take you to the archive. So yeah, it was released in 2018, thought it was. So let's have a little look at their hosted inference API. So as I said, it's trained on a masked language modeling task. So you mask out a token. So be careful here, it's not a word, you're masking out a token. And you're trying to predict what the missing token is. So let's just have a look at what this thinks is. So Paris is the blank of France, and they put capital with a very high probability. And you know, the output of this model, by the way, it's not just five tokens with a probability. It actually produces a probability distribution over your whole vocabulary. And it just happens that capital was the largest probability here by quite a long way. But perhaps let's put in another example where you're not actually you're gonna want back a token that's part of a previous word. So let's say I strolled along the river mask and full stop. And riverbank is actually one word. So here we see a hashtag bank. And the hashtag, that actually means that it's part of the previous token. So I strolled along the riverbank, one word. And that's assigned at quite a high probability. But you can see the other options here. I strolled along the riverbank, the river again, the river path, the river Thames. These are all totally, decent. It might be the real mask token, and I think that's the important thing to understand about the masked language modeling tasks is that there's not always going to be one correct answer. There's often the masked token could often be many things, and that's why when you're training BERT, you have to see lots and lots of examples. But at the end, you get this model that has a sort of inherent understanding of the language. So this is an example of a mask task, but what happens if we go to maybe a sentiment classification task? So let's go to text classification here under tasks, and we'll go to the distill BERT base uncased fine-tuned on this, I think it's Stanford Sentiments Tree Bank English task. So instead of trying to produce a probability distribution over the vocabulary here, we're going to be wanting to probably, either have a we probably want to have, since there's binary classification here of positive and negative, we're going to be want to have like a single neuron at the end of your neural network. That's going to be 1 for positive or 0 for negative, or you might have 2 at the end, something like that. And so here it's obviously put I like you, I love you, and it's put a very high probability to positive. But what happens if I put in I hate you? And you get very high probability for negative. And they probably, in the underlying code, they're going to use a sigmoid function or something like that. So you're going to be squished up to either 1 or 0. So this is all good. You can use these models straight out of the box if you like. And it's sort of fun to play around with the hosted inference API. But how do you actually use these models in practice? So you sort of have two options. You can either use the Hugging Face library itself, so they've got some useful pipelines for sentiment analysis, which we'll go through, or they've got a trainer class to train your own models, or the alternative is to sort of implement the models yourself with an existing ML framework such as PyTorch or TensorFlow. And I think they've started to support some more things as well. So let's just go up to resources here, and we're going to go down to the transformers documentation. So this is sort of a really, really useful section for when you're actually using the library, when you're going to be sort of trying to implement models. So down here on the left-hand side, they've got some guides using transformers, some advanced guides. And if you keep scrolling down, you'll find the model section. So although in the previous page I showed you they have lots of models, so there was that sentiment classification model, for example, that was fine-tuned on the Stanford tree bank dataset. Now that's a specific model, but here it's slightly different, slight tweak. It's actually the architectures that are supported. So the BERT architecture, or if I go down, I'll find the RoBERTa architecture down here. Where is it? RoBERTa down here. So you can go into these. So I'm just going to go back up to the BERT model just to keep it simple for now. So once you click one of these models, you'll see down here a list. So you've got a BERT model, you've got a BERT for sequence classification, and then you'll see these duplicates. You'll see, TF BERT for sequence classification, and that's talking about actually how the model is implemented. So TF is for TensorFlow, but the standard model is done in PyTorch. So we're going to be focusing on PyTorch in this series, and we're also going to be looking at some of the sort of inbuilt transformer stuff as well. We're going to have a look at their trainer in some later episodes. So let's go to BERT for sequence classification. So here you'll find the parameters to the model that you're going to need. You're going to find out what it gets back. You're going to see some little example code of how to implement it, and some other things. One other really useful thing is if you actually just go up to BERT sequence classification, you can just go to the source code itself, and you can have a little look at the source code, and this can often be maybe a good way to figure out what's actually happening when you're using the model, because it can sometimes be a bit black boxy and you're not really sure what's going on. You can also use this to have a little look at some, I don't know, what sort of BERT model names they have in this class. So you've got the large model here, you've got the cased, you've got the uncased, you've got a multilingual version, a Chinese version. So it can be pretty useful to have a look at this stuff. So now let's actually jump into some coding and have a look at how to, instead of just looking at the documentation or using their online inference API, let's have a look at how to get your own models into a runtime and use them. So let's just go here. I'm just going to connect this runtime on Google Colab. If you don't know what Google Colab is, then Google it and figure it out. It's really useful. It's just an online coding environment. But one thing that's really useful when you're using the Transformers library, if you're going to be retraining any models, you can get access to a GPU online for free. So let's just have a little run through. I've made a little example here. So first thing we're going to do is we're going to want to install the library. And I've just put this % capture here at the top. That just consumes any of that installation sort of dialogue that you normally get. I don't like that, so getting rid of that. So let's just have a little look here at their inbuilt sentiment analysis pipeline. So from Transformers import pipeline, we're just going to make a classifier for sentiment analysis. And I've made two example sentences here, a positive one and a negative one. I love dogs and I really hate dogs, so we know which is which. And also to note here, it says no model was supplied, so it's defaulted to distill BERT uncase fine-tuned on the Stanford sentence tree banks. And that was actually the model that we looked at earlier. So you can already see, maybe I could swap that out and I could maybe use a different one, train on a different task, on a different, sentiment analysis data set or something, for example. So now it's downloaded this model. We now have it in our runtime. So I'm just going to put in our positive and negative sentence and we'll have a little look. So the first one got labeled as a positive with a very high score. The second one got labeled as negative with a very high score. Exactly what we'd expect. So that's all well and good. We've used their sort of pipeline straight out the box, and we've sort of basically done what they have on the inference API, but we've done it in our own runtime. But now perhaps let's have a look at sort of getting one of those raw implementations of the model, and we can maybe do some more interesting things with it. So let's just have a little look down here. So from Transformers, we're going to import the auto tokenizer and the auto model for sequence classification. And that's also one thing that's quite useful about the Hugging Face library is they've got these auto classes. This auto tokenizer and auto model, that is basically just going to infer what is the best model and what is the best tokenizer to use based off the model name. So you see here I've actually used the same model that we've used here, this model, and I've just input this in as a string, and I'm just going to get this model back. So I'm just going to run that, and I'm also going to run the auto tokenizer to get a tokenizer, which will be based off the distilled BERT uncased model. But we could actually, instead of doing the auto tokenizer, we could use the distilled BERT tokenizer instead, and that's absolutely fine. It's the same thing because it's just automatically choosing it for us. If we were to perhaps do instead the BERT tokenizer, so I'll run that again. Perhaps we'll use the BERT tokenizer here, and what's it going to say? It's going to say the tokenizer class you chose. The tokenizer class you load from the checkpoint is not the same type as the class this function is called from. It may result in an unexpected tokenization. The tokenizer class you load from the checkpoint is the distilled BERT tokenizer. So this is just a warning that's saying, you've got it wrong. This model up here is using distilled BERT. You've tried to make a BERT tokenizer from a pre-trained distilled BERT vocabulary. So it's not going to work. I mean, it might work, but it's not going to work how you want it to work. So let's just change that back. You know what? I'm just going to probably get rid of that. And we're going to use this auto one. So let's have a little look at what the output is from this tokenizer. So I'm just going to put in my positive sentence, I love dogs. And what do we get back? We get a list of 5 numbers and this thing called an attention mask with 5 numbers in. So let's break this down. So we get special tokens at the start and the end of a sentence. So remember, I love dogs, it's 3 words, okay? But we get a beginning of sentence token and an end of sentence token, okay? And then this maps, in just this scenario, it maps to a 1-to-1. So I, the ID, the token ID for I is 1045. The token ID for love is 2293. And the dog's token ID is 6077. Let's maybe change this and we'll have a look at the negative sentence. Okay. And you know what? Let's do them side by side. So undo the pause and inputs neg. Okay. So we'll change that back to that. Okay. Let's have a little look here. So let's compare these. So we already had a look at the positive one up here. And now let's have a look at the negative one. So I is the same. Really, obviously there's no match. Dogs matches at the end, but I really hate dogs. And again, we have got a 1-to-1 mapping here, based on what the tokens were. But perhaps we have a token that's not, or a word that's not so common. So maybe I don't know, I thoroughly hate dogs. Okay, so I'm going to input these sentences again. We're going to have a little look at what they look like now. So did that go 1-to-1? It did. Okay, so that's not okay, let's choose something even more obscure. So swimmingly. I swimmingly hate dogs. Doesn't really make sense, but there you go. So let's work out our input IDs again. Here we go. Okay, so we've got something longer here than our input. So I is the same. Swimmingly, okay, is now two tokens. So we've got hate and we've got dogs at the end here, but swimmingly has been split up into two tokens. So what we can actually do as well is let's just put tokenizer, and then I think if we go from, I can't remember it off the top of my head, it's token IDs to tokens, tokenizer, Hugging Face. Let's have a little look at this. So we've got the tokenizer, and let's have a look. So convert tokens to string, convert IDs to tokens. Let's do that. So I think it's convert IDs to tokens, convert IDs to tokens, and we're going to give it a list, and we're going to put in our numbers here, and we're going to see what that outputs. There we go. So tokenizer, convert IDs to tokens, and we have swimmingly, and you see here again, we see that hashtag Lee at the end, and that's been split up because the vocabulary of DistilBERT in this example doesn't contain the token for swimmingly. So the way it actually breaks it up is it breaks it up into words that it knows in a greedy fashion. So it had swimming in a vocabulary, and it had ly, which is a common ending. And this can actually be done down to the character level. So if I just put in a little, absolute mess here, then we'll see what's reflected here as a much longer, here we go. It's just split this up in a crazy fashion. So let me try and get that here. So what's that converted to? That's converted this random string of characters into, it's split it up in this fashion. And then obviously I've actually just accidentally input in that last one, which was hate. So anyway, let's just go back to what we had. I really hate dogs. That was a little bit of a detour just to sort of explain how the tokenizers worked. So now we've got these things called attention masks as well. Now what are the attention masks? Well, in this scenario, I've tokenized input separately. I've tokenized the positive and the negative sentence separately, and so they have these attention masks that are of slightly different length. But what actually are they? Well, they're actually useful when you come to implementing or inputting multiple sentences into the model at once. Because of the way machine learning models work, you can't pass in variable lengths. So you can't pass in a short sentence and a long sentence together and expect the model to sort of adapt to that, because all that's happening in the back end is these large tensor operations, or matrix operations, if you will. And so what you actually do when you're using these models is you pad your input to a certain maximum length. So standardly it's 512 when you're training the model, but perhaps when you're retraining, you're going to need to have a shorter length, probably maybe 128 tokens in length. But what happens if so let's say we set the maximum token length to 128, or perhaps we set max token length to the largest sentence in our dataset, for example. What do you do to the other sentences? Well, you normally just pad them with zeros. And the attention mask is also used when you're calculating the loss. It's a sort of simple lookup. It's basically saying, okay, is my token ID in my sentence, is it actually a real token or is it a padding token? So let's have a little look at that now. So I've just created a little batch using our positive sentence and our negative sentence, and I'm going to say, okay, we want to pad these and we want to truncate them if they're too long, of a maximum length of 512, and I want to return tensors for PyTorch because that's the implementation we're using. I could, if I wanted to, change that to TF, and that would give me back TensorFlow tensors. So now we've done that, let's have a little look. So I've done PyTorch.attentionMask, and in fact, let's just look at the whole batch first of all. Okay, so the batch has returned me two things. It's returned me one thing, which is a dictionary. And inside the dictionary, we've got two things: input IDs and attention masks, just like we did up here in this when we're doing it separately. Except you'll notice now that the first example has had a 0 appended after the end of sentence special ID, and also its attention mask has got a 0 where the padding token is in relation to the input. Whereas my sentence with my maximum length, it hasn't been changed because it's the largest sentence in the dataset, and also the attention mask for it doesn't have a 0 in it because all of the input is valid. So now what we're going to do is we're going to pass this batch into the model itself. So we've just unpacked this basically into the model that we created up here, and then we're going to have a look at the output. So what we've done is we've passed this batch into the model, and now we're having a look at the outputs. So what have we got here? We've got a thing called logits. So logits, if you don't know, are basically just the raw output of the model. And often, especially for sentence classification tasks, you're actually going to want to apply a sort of softmax, or perhaps a sigmoid or something like that, but often a softmax to your logits, and that will amplify anything that is a large signal and basically sort of cancel out anything that is a weak signal. So now let's have a look at the predictions. Okay, so we've got a large number here. So we've got a 0.99971, and this is our first one, okay? And then our second one, we have the opposite. We have a very large value here, or not very large, but we have a 0.996 here, and then we have a very small value here. And this actually now compares to what we had in the pipeline up here. So our first example, which was marked positive, had a score of 0.9997. Our positive class here, so we've got back both our negative and our positive scores here basically. We've got 0.997. And if we go up and we have a look at the negative score for the second example, we had a 0.996. And again, we have 0.996 down here. So that's how we've actually got back the sort of raw outputs here from the model, given these two sentences, given the attention masks, and we pass them in together at the same time, and we've got the same output that we had from the sentiment analysis pipeline provided by Hugging Face itself. So yeah, so that sort of wraps up a really basic run through of how to use the Hugging Face model. In the next episode, we're going to be taking a model and we're going to be applying it to a more advanced task, and that's going to basically involve taking a data set and retraining a model from the Hugging Face. So we're going to use the RoBERTa model or something like that, and we're going to apply it to our own specific task, and that's going to involve retraining the model and then, you know, maybe adapting how it works at the end, because maybe instead of classifying one thing like positive or negative, maybe we want to classify a bunch of things. Maybe we have 8 classes. So stay tuned for that in the next episode. And in future episodes as well, we're also going to have a look at some masked language modeling tasks as well. And we're going to be using a PyTorch implementation for that. And we're going to retrain them and apply them to our tasks. So hope this guide has been useful for you. Let me know if you have any questions in the comments down below. And for any of the sort of technical background details about BERT or RoBERTa, I'll try and include some useful links that I found useful when I was first trying to understand the actual technical details of how the model actually works in the background. As I said, this sort of guide series is meant to be more practical focused, and it's going to be focusing on like implementing it with code rather than the sort of technical details of how the model works, because there's lots of good guides and lots of good lectures on how the models work in the back end, but I thought there was a bit of a lacking of sort of hands-on coding guides, getting up to speed with how to use the library itself. So thanks for watching, and let me know if you enjoyed it. Cheers.